Okay, so we're making good progress here with our stoichiometry. Let's move on to our next problem. What mass in grams of copper would be produced in this case? Okay, so we can begin our problem as we were before. We're starting with 28.2 grams of ammonia. So let's remember where we began. 28.2 grams of ammonia. And we want to know this time the mass in copper. So over here, I want to have an answer that is in grams of copper. Okay, so the way I'm going to do that again is use my balance equation. And the first step is always to convert to moles if I'm not already in moles, because our equation is given in moles. We can't use our equation unless we use moles. So again, we will put the mass of ammonia on the bottom and the moles of ammonia on the top. And this is just our molar mass of ammonia, which we had written up here, 17 grams per mole, a number we got from the periodic table. All right, that's converting our grams of ammonia to moles of ammonia once again. And in this case, next, we want to figure out how much copper. So we want to put our moles of ammonia on the bottom. And the moles of copper we'll get on the top. And we always check our balanced equation to see what numbers we put here. So our balanced equation says that for every 2 moles of ammonia that react, we create or produce 3 moles of copper. So the 3 goes on the top. And then finally, the answer they're looking for is in moles. So we have to use our mass of copper in order to convert back to mass. That's copper. Oops. Copper. So let's just look back and remember what the mass of copper is. 63.5 grams per mole. There, we'll put that there. 63.5. Right? Maybe before we do our math, we can just make sure we've converted grams to moles by using the molar mass of ammonia. Then we've converted moles of ammonia to moles of copper by using our stoichiometric coefficients from our balanced equation. And then we're converting moles of copper to grams of copper using the atomic mass of copper. Okay, so we want to use our calculator correctly. We start off by 28.2 divided by 17 times 3 divided by 2 times 63.5 equals, I'm getting 158 grams. 158 grams of copper. So it seems like a lot of copper. So there we go. We've got another one, and I think we have one more question to do in this series. Let's see. If the water produced is cooled and collected, the percent yield is 90%. Okay, so let's imagine that then. We're doing this reaction, and it must be at high temperature because we've got ammonia, gas, nitrogen, of course, is a gas. But water is not a gas at room temperature. It's a liquid, so we must be higher than room temperature. If we cool it down, though, this will condense and form liquid water. What's the volume of water contained? And in order to get that, we'll need to know the density of water is 1.00 grams per milliliter. Now, we could go back to the beginning, as we have each time. It started with 28.2 grams of ammonia, but maybe we can just start with something else, right? We've already converted this to grams of copper, right? And so maybe we can just try a different way to solve the problem, right? So we know that when we start with 28.2 grams of ammonia, we get 158 grams of copper. We also get 0.829 moles of nitrogen. That might be the easiest one to start with, right? So we know we get 0.829 moles of nitrogen. So why don't we do that? 0.829 moles of nitrogen. That's how much nitrogen we get. If we get that much nitrogen, how much water do we get? Well, we can tell because we can see here that for every mole of nitrogen, we're going to get 3 times as many moles of water. And then if we convert our moles of water to mass of water, remember that water has a molar mass of 18 grams per mole. So 1 mole of water is 18 grams of water. In this case, we want to know the volume of water, right? So we need this conversion of 1.000 grams of water is the same as 1.000 milliliters of water. Okay, is this going to give us the volume of water? Well, this would give us the volume of water if everything goes perfectly. We're told it goes only 90%. But let's calculate our theoretical yield, and then once we take 90% of that, that'll tell us how much we actually have. So again, all I did here was kind of start in a different place, right? I knew from the couple problems ago that the number of moles of nitrogen I get is 0.829. So I've just saved a step of converting from ammonia again. So 0.829 moles of nitrogen is what I started with. That's how much I get in this reaction. And if I get that much nitrogen, I know how much water I get because I'll get 3 times as many moles. We know that from the stoichiometry of the reaction. Once I know my moles of water, I can convert to grams of water, and because 1 gram weighs 1 milliliter, I can then get my volume of water. So let's make sure our moles of nitrogen cancel, our moles of water cancel, our grams of water cancel. So we should end up with milliliters of water, which is a volume, right? So they want to know what's the volume. So 0.829 times 3 times 18 times 1. Looks like 44.8. 44.8. So you'll notice I've carried through my 3 significant figures because we started out with those 24.3 grams of ammonia, which was 3 significant figures. So that's my theoretical yield, 44.8. But I know I'm only going to collect 90% of that. 90% of 44.8 equals the volume I'll get if the yield is 90%. Now, why might it be 90%? You know, you're condensing the water, maybe some of it escapes your vessel or something like that. So here on our calculator, we can just put in 90% times 44.8, and we get 40.3 milliliters of water. Okay, so here we've done several stoichiometry problems. We used a balanced chemical equation to calculate the amounts of reactants or products needed or expected. And we did that for several things in this particular reaction. The key was to balance the equation using these numbers in front, which are called stoichiometric coefficients. Those tell us the ratio in moles of how this particular recipe goes, right? For every 2 moles of ammonia, we need 3 moles of copper oxide, and that's going to produce 3 moles of copper, 1 mole of nitrogen, and 3 moles of water. And so we can do all sorts of things, start with different amounts of different things, and figure out different amounts of other things, and we use the same kind of process. We start with what we're given, we end up with what we want, we make sure we understand every conversion factor and where it comes from. Typically they're going to come from the balanced equation, those give us our mole ratios, or they will come from molar masses, we get those from the periodic table, or there might be some other information that's important, like the density, right, converting mass to volume. And also, if the yield is not 100%, we have to account for that. And we can do that, as we did in this problem here. Stoichiometry is a lot of fun, and it also helps you if you're in the kitchen baking.